In this module, we'll turn blockchain buzzwords into concrete architecture. We'll connect familiar elements, cores, ledgers, payment hubs, and channels to blockchain nodes, gateways, and custody services. By the end, you'll be able to sketch a realistic on-chain payment stack for your institution. When you put cross-border payments on-chain, you are not replacing your bank's system of record. That still remains the authority. Core banking ledgers hold the balances your regulators, auditors, and finance teams rely on. Sub-ledgers sit underneath as the detailed, regulatory, and reporting source of truth. Anything on-chain must reconcile back into those records, either in batches or near real-time. So as you evaluate solutions, keep asking, how does this flow get reflected, controlled, and reported in the existing ledgers? A payment hub acts like the air traffic controller for payment instructions. Multiple channels send in messy, inconsistent messages. The hub standardizes them into a common format. It then applies routing logic, pricing, risk, and compliance rules. From there, it chooses the rail, Swift, RTGS, or a blockchain rail, to get the best mix of cost, speed, and control. Adding new payment rails shouldn't make your customer edge more complicated. Every channel your clients use, mobile app, corporate portal, host-to-host, or API, should feel like a single facade sitting over many rails. A strong payment hub hides that complexity, so product teams can swap or add rails without breaking the experience. At the same time, you expose only what customers care about: clear cutoff times, fees, FX expectations, and confirmation status, ideally in real time. Nodes are your institution's gateway into a blockchain network. Every on-chain payment your systems initiate or monitor ultimately flows through a node. It accepts transaction submissions, relays them to the network, and reports back confirmed results. It also answers questions like, what's this balance now? Because of that, node uptime, latency, and behavior during chain reorganizations directly influence payment reliability. Choosing how to access a blockchain is really a trade-off between control and simplicity. Self-run nodes give you maximum sovereignty. You decide upgrades, security posture, and uptime. The cost is a heavy operational burden and more complex integrations. Vendor-managed nodes reduce operational work, but create dependency on that provider's reliability and controls. API gateways are the lightest to run and the fastest to integrate, but you accept deep reliance on a third party for both security and network access. When a bank uses blockchain, it rarely talks directly to the chain. Gateways and custody platforms sit in front, hiding raw node complexity and turning it into familiar controls. They enforce who can move what, when, and how much. With multi-party computation, no single device or person can move funds alone, sharply reducing single points of failure. Middleware becomes the central nervous system that links your legacy stack to on-chain rails. API gateways manage security and service exposure, making sure only authenticated flows reach your blockchain components. Event buses like Kafka move payment events around in near real time, so systems react to changes instead of polling. Orchestration engines then coordinate these steps into a reliable state machine, ensuring every off-chain and on-chain action happens in the right order, with clear error handling and auditability. Once your core systems connect to a blockchain node, you'll choose between synchronous and asynchronous patterns. Synchronous flows use simple request response. The payment hub calls an API, waits for a result, then proceeds. It's intuitive, but each dependency adds latency and a risk of timeouts. Asynchronous flows treat the blockchain as event-driven. You submit a transaction, persist the request, then react to confirmations via callbacks or queues. In both cases, idempotency is essential. Every message must be safe to retry without accidentally posting the same payment twice. On-chain payment flows should assume failure and be designed for graceful recovery. Automatic retries with exponential backoff handle transient issues like short node or network outages without hammering the chain or upstream systems. If a step has already posted to a ledger and later fails, you don't edit it. You compensate it with an explicit reversing entry. Anything that still doesn't match is routed into reconciliation queues for human review and root cause analysis. A reconciliation engine keeps your blockchain pilot tightly aligned with your books. It continuously compares on-chain balances and transactions with your internal ledgers, flags, mismatches, and routes them into an exception workflow. Think of it as an always-on auditor, ingesting events from the chain, translating them into your internal data model, and proving that what the chain says matches what finance reports. Without this layer, scaling on-chain settlement will quickly break accounting, reporting, and ultimately trust. This diagram brings the components together into a single hybrid stack. On the left, customers and channels look almost unchanged. Their instructions still reach your existing core banking and payment hub. The key difference is in the middle. A middleware layer decides when to route a payment on-chain, manages retries and fallbacks, and keeps your legacy systems in sync. On the right, custody and gateway services hold keys, sign transactions, and connect securely into one or more blockchain networks for final settlement. Treat this as an architectural sketch, not a final production design. Start by listing the cores, payment hubs, and customer channels that already touch cross-border flows. Then add the new blockchain components, nodes, wallets, or custody, and any gateways or vendor APIs. Connect them using your existing middleware and message buses. As you do, watch for unclear monitoring, reconciliation, or ownership. Those gaps become your first set of design and control questions. Designing for enterprise reality means balancing three pressures. First, performance. Latency, throughput, and availability must match or beat existing rails. Second, security and compliance. Keys, data, and access have to follow jurisdictional and regulatory rules. Third, the operating model. Clearly defined roles for IT, treasury, and operations. So responsibilities are shared, handoffs are clear, and nothing falls through the cracks.